common term that lies in all the news is either EV or hybrid vehicle variant. So all put together, I just thank the coordinator for picking this particular topic for the faculty development program and the research community. So where you can just see this EV and hybrid vehicle variant are there in news for past 1 year and above. So this put an immediate pressure among all the researchers and faculties to think about what is the basics of hybrid vehicle or electric vehicle and how it is going to propel in the upcoming years. So that is must be very much that should be very much be clearly understood by the research community at this point of time. So the vehicle population in near future talks about the variation in the vehicle sold at this particular point of time. By 2010, if you just see the number of vehicles sold was dominated only by internal combustion engine. So either it can be pure petrol variant or pure diesel variant. But as the year keep on increasing, you can just see the percentage of the internal combustion engine have slowly stopped to get degrade. So it means that the percentage of sales based on pure petrol or diesel variant is slowly stepping down at this particular point of time. And this would be dominant by either plug-in hybrid vehicle or pure hybrid vehicle. So HV stands for hybrid vehicle. So hybrid vehicle is the combination of both a fuel-based energy source and electrical energy source. So for upcoming next 10 to 20 years, you can just see most of the vehicles would be alive only by the name of hybrid vehicle variant, but any of the future scope would be dominated by only electric vehicle. So this is what is the current population scenario of vehicles, particularly in India and all around the world. So internal combustion engine will be alive only by the name of hybrid vehicle and not as pure internal combustion engine. So this is what is the current scenario, and that is going to be the future part in the upcoming years. And talking about the history of hybrid cars, nothing is new under the horizon. Either it can be an electric, hybrid, or pure internal combustion engine. So all has been initiated at the same time scale only. So it was merely 100 years back as of now. So it was in 1832 the first crude electric vehicle was developed, and at the same time scale of 1893, the gas power internal combustion engine was commercialized. So if you just see that it is all happening in late 18th century, and if you just see very keenly, the first hybrid electric car is invented in the time scale of 1901. So all happens at the same time zone where either it can be electric or internal combustion engine or hybrid vehicle. But among these three competitors, only pure internal combustion engine dominantly rule the world for past 100 years, whereas the electric vehicle and hybrid vehicle was suppressed to a greater percentage at this particular point of time. So what actually happened at that particular point of time is because of the easy availability and reduced refueling time, all put together make internal combustion engine as a key leader in the automotive field. But as year keep on propel, the gas price and the fossil fuel price is keep on skyrocketing. So this accelerated the researchers to think an alternate source of energy. So thereby the role of electric vehicle or plug-in hybrid vehicle was once again there in the picture. So it was in 1997 the first mass-produced hybrid vehicle was introduced to the automotive field. So it took nearly 100 years. So the hybrid electric vehicle was invented in 1901, and whereas the mass production was of first hybrid vehicle took place nearly 100 years to get commercialized. So for past these 100 years, only the pure internal combustion engine was ruling the whole automotive market. But there comes the hero of our current scenario, which is a Silicon Valley based startup. So Tesla Motor, a Silicon Valley based startup, announced it will just produce a luxury electric sports car. So people were as of now thinking about either internal combustion engine or hybrid vehicle to sustain the fossil fuel based as a basic energy source. But in 2006, and startup came up with a very huge idea that they will just produce a luxury electric sports car which ranged to a distance of 200 plus miles, which is enormously high at that particular point of time, and they have just even achieved much more better in this current scenario. So this accelerated all the automotive manufacturers so to propel their research and development team to focus on the electric vehicle or hybrid vehicle from this particular point of time. So thereby, where the automotive manufacturers have started to think about even Maruti Shift Desire, which is an high-selling vehicle, especially in India, or Maruti Shift or Shift Desire variant is where most of the people preferred vehicle in India. So they have come up with their plug-in hybrid vehicle variant in Australia. So sooner or later they might also have an hybrid variant in India also. Even Maruti Sia's variant is coming with an hybrid format. So it is that all the internal combustion engine is slowly getting converted into this hybrid vehicle market, or they will just switch over to EV. So this is what is the current scenario of the automotive field lying with hybrid and electric vehicle scenario. And let me just give a brief introduction about what is this hybrid and electric vehicle. So thereby you can just have a clear vision. So the battery powered electric vehicle, on the other hand, possesses some advantage over pure internal combustion engine, such as high energy efficiency and zero environmental pollution. So one thing you should be very much clear that the zero environmental pollution is mentioned from the user end. So it is not that it is that whatever the vehicle that you have won't emit emission. So from the user end, you can just justify the statement that it results in zero environmental pollution. So, but in a broad way, if you just think about how the electricity is produced for propelling this EV, so for this propulsion or for this electricity generation, you need to focus on the power plant. So whatever the present scenario says that when the electric vehicle has penetrated to a greater extent in the automotive field, particularly in a highly populated country like India, so the demand for electricity would be keep on increasing. So in a nominal percentage, accordingly, I think so the price of an unit current in an in an Indian region would cost from around 5 rupees 50 pies to 10 rupees. So that would be the cost of an electricity per unit. So, but when the demand is keep on rising based on the penetration of EV, so the demand for the power plant based on electricity production would also keep on get increasing. So for that, you need to give excess amount of uh, the feedstock. So that would be nothing but either it can be fuel source or biomass, whatever it is. So rather in this particular scenario, if the electric vehicle penetration is enormously high, the end user vehicle won't emit emission, but the power plant would emit an excess emission to handle this particular demand. And if the electric vehicle penetration is enormously high, the cost of electricity would also gradually increase based on the time scale how the electric vehicle penetration happens in the next upcoming years. So this would be one of the major threat that we might face in the upcoming years. So if the penetration of EV is greater in next 3 to 4 years. So however, the performance, especially the operating range per battery is far less compared to the internal combustion engine. So this is one of the key reasons why people have not completely switched over to EV at this particular point of time, because whatever the energy that you can just drain from a battery is far less as of compared to your petrol or diesel variant. So it was in the time scale of either 1900 or 2020 or even now. So the energy that you can just grab it from gasoline is merely 12K. But whatever the lithium ion battery that you have can able to deliver only a power source of just 4K, 400. So which is a huge difference as of the energy density or the energy capability that a gasoline and a battery can deliver. But thinking about the weight, it also says us far below impact on your electric vehicle. So the lead acid battery would weight to an mass of merely 10,000 kg in year 1900, but as of now they have dealt with a very much research progress in the weight reduction, where you can just see the weight has been drastically reduced from 10,000 kg to 200 kg. But even though when you are just switching or dealing with an electric vehicle, you should obviously carry an excess weight of around 200 kg that particularly focus on battery weight. But even now, the research are even further progressing to reduce the weight of the battery and overall system. So that is on the research progress. But in a broad way, the greater disadvantage that focus on the EV, particularly only pure EV, is one is energy density, second one is the weight, and the overall cost of your electric vehicle would be typically 50% delivered only to the battery and its respective system. So for if you think about, you are just purchasing a vehicle for around 100 lakhs, 50 lakhs you need to deliver, or you need to particularly allocate for your battery system alone. So this is a huge amount of investment for your battery based vehicle. So that is why people are thinking about clubbing both the advantage of internal combustion engine and the battery. So the hybrid vehicle variant is which uses two power source. So this two power source talks about the primary power source will be obviously internal combustion engine. So at any point of time, the percentage of the power that the battery deliver won't exceed the 49%. It means that the primary power source would be purely internal combustion engine, and only the secondary power source will be your electric vehicle. So only the secondary power source will be electric vehicle, and the primary power source will be pure internal combustion engine. So talking about the types of EV, either it can be a hybrid electric vehicle, are plug-in hybrid electric vehicle, or pure electric vehicle, and in future it would be focusing on fuel cell and solar based vehicle. So this solar based vehicle would be the only option when the electricity price is predicted to rise above 10 rupees per unit. If the electricity price is keep on increasing, you need to rely on some renewable source of energy rather depending on the grid based electricity. So if that is the case, people would think about making use of solar based energy for electricity production and its propulsion. In a broad way, hybrid electric vehicle variant is further branched out into series parallel and series parallel. So in this case, you will be making use of both the fuel and the electric motor as an power source. So you'll have an internal combustion engine and an electric motor, and this electric motor can be powered either from a battery power source, or it can be from externally charged plug-in base variant. So the internal combustion engine will be alive for the next 20 to 30 years only by the term of hybrid electric vehicle and not as pure internal combustion engine. And once you are just moving away from internal combustion engine and focusing on pure electric vehicle, it can be a plug-in type, and further the research would be extended on fuel cell based vehicle and solar based vehicle. So this is how the futuristic electric vehicle model would be designed. So even if you just see, all the vehicle variants are slowly get switched over into the hybrid vehicle variant. So if you just see Maruti Ciaz variant, it's most of its variant are coming with the hybrid classification. So either it can be mild, micro, or full hybrid. So we will discuss further about what is this mild, micro, and full hybrid. And sooner or later, they are also coming with a pure electric vehicle. So Maruti has pledged that they would come with a pure electric vehicle variant by 2025. And in later years, you need to focus only on fuel cell and solar based vehicle. So this is what the earlier graph that I have explained. So in next 5 to 10 years, all the vehicles would be get switch over into the hybrid vehicle, and later as pure EV, and further as an alternate source, just relying on the grid-based electricity. People will be thinking about generating their own electricity by means of either fuel cell or solar-based vehicle. So this is how the types of EV would be classified in this particular scenario. And what is this degree of hybridization? So the term, the vehicle hybridization, is mainly classified into three. One is micro hybrid, second one is mild hybrid, and third one is full hybrid. So this talks about the percentage of the electricity dominance or the power drain from your electric motor, talks about the degree of hybridization. So let me just brief up with this small pictorial representation. Assume you are having a demand of 100 kilowatt power. You are having a demand of 100 kilowatt power, and if 75 percentage of power is delivered by your internal combustion engine and 25 percentage of your power is able to deliver from your electric motor combination, then the degree of hybridization is 50 percentage. Then the degree of hybridization is 50 percentage. And in the vice versa case, if 50 percentage of power is delivered from your electric motor and 50 percentage of power is delivered from your internal combustion engine, that means that your degree of hybridization is 50. And in the next stage, if it is 75 percentage, if 75 percentage of power is delivered by your electric motor and only 25 percentage of power is delivered by your internal combustion engine, then your degree of hybridization is 75 percentage. And if the overall power is delivered from your electric motor, it is pure EV. So our stand would be exactly at 50 percentage. So to make your internal combustion engine is alive, to make your internal combustion engine alive and um, make it as a primary source of energy, the power that drain from your electric motor should not exceed above 49 percentage at any point of time. If it exceeds 50 percentage, your electric motor would be your primary source of energy and your internal combustion engine would be your secondary source of energy. So as of now, whatever the hybrid vehicle variant that is designed would have a percentage between 0 to 50. So whatever the classification that we are going to focus on talks about this percentage of degree of hybridization. So either it can be 0 to 20 percentage. If it is 0 to 20 percentage of degree of hybridization, then your vehicle can be known as micro hybrid. If it varies from 20 to 30 percentage, your vehicle would be coined as mild hybrid. And if the percentage varies from 30 to 50, your vehicle would be coined as 50 percentage. If it exceeds 50 percentage, then your vehicle would be converted into an electric vehicle where your primary energy source would be electric motor. So sorry for it. So we have not moved into that particular point of classification. So this word talks about the term degree of hybridization uh, in the hybrid vehicle variant. So now we'll just see very clearly about how it is going to support your vehicle. So whatever the two-wheelers that you have, so all the two-wheelers that you have now, it is coming with an option of power start. So whatever the vehicle that you have, now it is coming with an option of power start where you won't be kicking your vehicle to make the first ignition. So even this particular of optimization is known as the mild hybrid variant. So talking about mild hybrid variant, you will have an internal combustion engine and an electric motor, and this electric motor will be assisting you in your start and stop operation. If you are just making use of your electric motor to start and stop your vehicle, then you can just coin your vehicle as a micro hybrid vehicle. As a micro hybrid vehicle, sorry for it, I have mentioned it as mild. So it is known as a micro hybrid vehicle. So all the two-wheelers that is there in the market is having, if it is having a power start operation, then you can just coin your two-wheeler as an hybrid vehicle variant, which is known as a micro hybrid variant. And in addition to the start and stop operation, if you are having an option of electric motor, you can just think about the regenerative braking. So where you can just try to convert your motor into a generator and store the energy that is typically wasted as and heat in terms of kinetic energy at the time of braking. So this particular add-on advantage can be obtained when you are just clubbing an electric motor to your existing internal combustion engine. And you can just see the percentage of internal combustion engine has slowly stepped down when an add-on advantage is getting clubbed with your electric motor combination. So this what talks about the micro hybrid classification where the hybridization, sorry for it. I hope, can you hear me clearly, sir? Am I audible, sir?
Yes, sir.
Yes, sir. You are audible, sir. Audible.
Okay. I hope I received some message stating that I was not audible. Okay, no issues. So the next is the mild hybrid. So the micro hybrid, the degree of hybridization varies from 0 to 20%. When moving over to mild hybrid, the percentage varies from 20 to 30. So in terms of 20 to 30, apart from start and stop operation and regenerative braking, certain amount of power would be delivered from your electric motor for the propulsion. So if you are able to deliver certain amount of or grab certain amount of power from your electric motor for the vehicle propulsion, then you can just coin your vehicle as mild hybrid vehicle. So Maruti Suzuki's variant are coming up with this mild hybrid vehicle variant where it is able to have a lithium-ion battery and a lead-acid battery combination for delivering certain amount of additional power for the propulsion. And next is full hybrid variant where the percentage varies from 30 to the percentage varies from 30 to 50 percentage. So if the percentage varies to 30 to 50 percentage, then you can just coin your vehicle as sorry for the interruption. So the next percentage is the full hybrid variant where the percentage varies from 20 to 30 percentage. So apart from start and stop operation, regenerative braking, power assist, a short electric drive particularly can be incorporated to your system. So you can just able to deliver excess amount of power from their battery source. And next is the option of plug-in hybrid variant where apart from charging your battery from internal source of energy, you can just able to charge your battery from external source of energy. So that what talks about the plug-in hybrid variant. So in all these cases, you can just see there is a term known as a downsize of your internal combustion engine. So that is what we are going to focus on. So when your internal combustion engine is getting a transformation into an hybrid vehicle market, so your internal combustion engine won't be alive as it is. Your internal combustion engine need to be get modified to get adapted to this particular environment, which is going to be dominantly a pure electric vehicle based market. So if that is the case, your engine need to be downsized and get an performance upgradation to handle this particular scenario. And once you are just getting switch over from hybrid vehicle to pure electric vehicle, so your internal combustion engine would completely get ruled away. So based on a detailed prediction, it would be expected that till 2040 or 2050, your internal combustion engine will be alive only by the name of an hybrid vehicle variant and not as pure internal combustion engine. So I hope now you have a clear vision about what are the different classifications of hybrid vehicle variant, particularly and the add-on advantage when you are just clubbing with an internal combustion engine and an electric motor. And we will focus more on this particular term. What is engine downsized and how your internal combustion need to be get tuned to get adapted to this particular environment in the upcoming slide. And the conceptual illustration of your hybrid electric drivetrain talks about you are going to club two energy sources into one unit. So first energy source, let us just assume it can be a fuel, either it can be a petrol or a gasoline or diesel variant, and you will have an internal combustion engine, so that is your energy converter. And in the second option, you will have a battery as an energy source, and your energy converter would be motor converter generator, and this is the load that is demanded from your end wheels. So either it can be option one where the power source can be drained from fuel internal combustion engine to handle this particular load, or it can be either from battery electric motor to handle this particular load, or it can be able to combine both. If you are just trying to combine both, it would be an hybrid vehicle variant where at certain point of time, as I said earlier, this electric motor would assist you to handle that particular load. So when talking about getting hybridization, there are these 9 different modes at which your vehicle can be able to run. So first one is engine alone propulsion mode. If it is engine alone propulsion mode, based on your demand, the power flow would be from the fuel and next to your internal combustion engine. From there, the power would be delivered to your end wheels. And the next one is pure electric propulsion mode. If it is pure electric propulsion mode, the power would be in this fashion where it would be from battery, from that to motor, and the motor would be able to deliver the power demand that is required in the end wheels. And third one is hybrid traction mode, where you will be able to club both the internal combustion engine and the electric uh, base combination to handle the particular demand that has been raised to your end wheels. And third one is regenerative braking mode. So in the point of regenerative braking mode, you can just see an arrow is moving back to the energy converter to in the reverse direction. It says that based upon the end wheel rotation, certain amount of power can be retrieved back to your energy converter 2. So that is where the motor will be acting as a generator, and that energy can be used to charge your battery. So that what talks about the regenerative braking mode. And these are the different combination of modes where the engine will be able to charge the battery while the vehicle is running. Both the regenerative braking and internal combustion engine charge the battery simultaneously. Engine propel the vehicle and charge the battery, and engine charge the battery. And the power flow into the battery from heat engine through the vehicle mass. So these four talks about how the charging of your battery would be able to handle if it is not a plug-in hybrid vehicle variant. If it is not a plug-in hybrid variant, then you need to uh, particularly focus on how you are going to charge your vehicle, because you doesn't have an external energy source to charge your battery. So you need to charge your battery at the time of either internal combustion engine running, or at the time of your regenerative braking mode, or simultaneously you need to do both operations. So these are the major 9 modes that would be actually happening in your hybrid vehicle variant if it is not a plug-in hybrid electric vehicle variant. If it's a plug-in hybrid electric vehicle variant, these 4 options can be skipped off, and you can much more focus on the first 3 options to get a better performance. Because if you are able to drain certain amount of power to charge your battery, then there would be a power reduction. So that can be very much understood in the Shanky plot that I have come up with in the next slide anyhow. So this what talks about the conceptual illustration, how the electric drivetrain can be operated in different modes of operation in your vehicle. So next, broadly, you might have heard about the classifications of hybrid electric vehicle variant as series and parallel, and series parallel combination. Even uh, whatever the vehicle that I have explained earlier, Toyota Prius comes with a combination of series parallel, whereas series and parallel are just old school books. So series parallel is what the Toyota Prius have come up with, and now they are just dealing with complex uh, hybrid drivetrain combination to deliver a better performance as of now. So these series and parallel are just old school books, so they are not used majorly as of now. In case of series hybrid drivetrain, you will have fuel, engine, and from the engine the power would be get converted through a generator, and this electricity would be given to your motor controller, and this traction motor propels your vehicle. So this series hybrid vehicle would be more or less an electric vehicle where rather draining the power from your battery, you would be able to give electrical energy from your internal combustion engine. So that's what talks about the series hybrid drivetrain. And this would be the pictorial representation of it. You will have a fuel, internal combustion engine, from there a generator within power electronics, and this would be able to deliver the electrical energy to your traction motor, and that would be able to rotate your end wheels. Additionally, you will have a battery to this particular combination. So this is nothing but an electrical coupling. So in general, the series hybrid drivetrain would be named as an electrical coupling combination, where you would be coupling both electrical energy from the battery and the internal combustion engine based electrical generation unit by through a generator would be coupled together to deliver the end wheel demand. So this can be either an engine alone mode, or battery alone mode, or engine plus battery and engine charging and regeneration. So that's what I have explained earlier based on different modes that normally a hybrid vehicle would come up with. So the overall mechanism is very simple, and an optimal internal combustion engine speed can be attained. So this is not as of now used in a broad way. And looking into the power plot in a brief manner. So this can be coined in the similar fashion as it can be either a traction mode or braking mode. In terms of traction mode, it can be either pure internal combustion engine alone mode. If it is internal combustion engine mode, the battery the electrical energy from the battery would be cut off, and only the electrical energy from your internal combustion engine combination would be delivered to handle the demand at the end wheels. And if it is pure electric vehicle mode, that is pure battery only mode, so the internal combustion engine would be completely get switched off, and the power source would be delivered from your battery to handle the end wheel demands. And third one is the hybrid traction mode, where the power would be delivered from both the internal combustion engine and the battery to handle the end wheel demand. So this is how an hybrid vehicle mode, traction mode would be looking like. And this is off charging mode. So certain amount of power would be delivered from your internal combustion engine to charge your battery according to the battery state of charge. So SOC would be keep on monitoring. If the SOC falls below zero point 0.3 or zero point 0.4, certain amount of power would be delivered from your internal combustion engine based electrical energy to charge your battery. And next one is the regenerative braking mode. In case of regenerative braking mode, certain amount of power from the end wheels would be given to charge your battery. So this what talks about the series hybrid drivetrain in a brief manner. And next move into parallel hybrid drivetrain. So the word parallel refers to the term that we are going to combine both the internal combustion engine and electrical mode in a parallel way. So the word parallel refers to the fact that the torque from electric motor is added to the torque from internal combustion engine. So that is the total torque propel the vehicle. So in the series hybrid, it is more or less a pure EV vehicle variant, because we are only the electrical energy delivered from either battery or the internal combustion engine is going to propel the traction motor. But this is an inverse case where either pure internal combustion engine can be able to propel your end wheels, or the combination of both can be done. So in general, there are five different points at which you can just club your electric motor and battery combination to your existing system. Either it can be before the internal combustion engine. In most often cases, they used to prefer this. So this is where the micro hybrid variant would be looking like. So whatever the two-wheelers that you have, all are kind of micro hybrid based vehicle. So what they will try to do is they will just try to remove the alternator in your existing system and come up with a motor, and that motor would be acting as a generator, and that would be connected with the engine crankshaft at the front end. So this would be able to start and stop your engine. So this is one of the easy part by which you can convert your existing internal combustion engine into an hybrid vehicle variant, that is particularly a micro hybrid variant, because you doesn't need to make any drastic change in your existing system before, because you can just drain power from both the sides of your internal combustion engine. In the frontal part, you are going to deal with an motor and a battery combination. With this, you can just state that your vehicle has been converted into a micro hybrid based vehicle. And next one is before the clutch, after the clutch, after the gearbox, and at the end wheel. So there are different combination, and each and every combination is having its own advantage and disadvantage, and why it is highly preferred. So we won't move further into it. These are at different points at which you can just combine your battery plus motor combination to handle or convert your existing internal combustion engine into an hybrid vehicle variant. So here I have just picturized uh, the pivoting point 3, where your battery, inverter, and electric motor is placed after the gearbox. So you will have a fuel tank. From there, the fuel will be supplied to your internal combustion engine by means of clutch, at which the torque variation or the torque conversion can be happen by means of a gearbox. From there, by making use of a mechanical coupling, the power would be delivered to your end wheel demand. So this is where you can just deal with either pure internal combustion engine mode, or by means of battery, inverter, and electric motor, you will be able to deliver your demand by pure EV, or you can just try to combine both by use of this mechanical coupling device. So this would be most often case an epicyclic gear train. So your pure series hybrid drivetrain is known as electrical coupling device, and the parallel hybrid drivetrain is known as mechanical coupling device because of this particular combination where your internal combustion engine and electric motor would be clubbed together by means of a mechanical device. So that is the reason why often your parallel hybrid drivetrain is known as a mechanical coupling device. And this gives you the Shanke plot of your parallel hybrid drivetrain power flow. So you are having internal combustion engine, gearbox, and after the gearbox, you are having the battery, inverter, and electric motor. If it is pure internal combustion engine battery, the power source would be delivered from your internal combustion engine, and the power would be delivered from your electric motor. So this would be the overall power. So let us just mention this particular value as L. And either if it is pure internal combustion engine, the value or the overall case of this is L1. So you can just clearly see that the distance between these two pointing point L is greater than L1. So if it is a combination of internal combustion engine and battery, you would be able to deliver an excess power, and when it is rather focused on pure internal combustion engine. And if the SOC falls below zero point 0.3 or zero point 0.4, you need to drain certain amount of power from pure internal combustion engine and charge your battery. If that is the case, the power would even further drop down than the previous case. So assuming this was L2, so L1 is greater than L2. So certain amount of power need to be drained from your internal combustion engine energy to charge your electric motor and battery combination. If that is the case, what actually happens is uh, the overall demand that is raised on your end wheels cannot be effectively handled. So that is the one of the reason why people are slowly moving into plug-in hybrid vehicle variant to optimally charge your battery and optimally have an extended range of battery to have a better output. And next one is the battery alone mode. Here you can just see your internal combustion engine is completely switched off and only the power is delivered from your battery to handle the end-wheel demands. And this talks about the engine braking where the power source is not given to your battery plus motor combination, and in case of regenerative braking, the dominant amount of energy would be given to your battery plus motor combination to charge it. So in general, either it can be series hybrid, parallel hybrid, mild, micro, whatever it is. This type of Shanke plot will give you a clear idea about how the power flow lies between the starting point to end point to handle the end wheel demand. And normally it would be divided into two cases. One is the traction mode and second one is the braking mode. This braking mode gives you an idea about how the charging will also happen when you are just dealing with an electric motor and battery combination. I hope now you are having a clear vision about the parallel hybrid drivetrain. And as I said earlier, my focus would be much more dominantly focused on engine downsizing. So as I said earlier, the diesel engine or pure internal combustion engine is slowly getting suppressed to a greater level, and we need to focus on a better engine to sustain in this particular market for next 20 to 30 years. So for making your internal combustion engine alive, you need to focus on one particular term is that engine downsizing. So this engine downsizing has nothing to do with its performance. So engine downsizing says that you won't reduce the performance, but simply it is a method to use to reduce the weight to its minimal possible percentage and to breed power to weight ratio and make it much more efficient. So the overall objective is you are going to reduce the weight of the entire system, and that should be able to deliver the same output. So consider this is the earlier engine which is able to deliver 60 kilowatt power and hoping and weight of around 200 kg. And the term engine downsizing means you should deliver at least a power limit of 55 kilowatt with a reduced weight percentage of around 150 kg. Sorry, of around 220 kg. So you have somehow compensated the weight to a minimal extent. So you have drastically reduced the weight from 200 kg to 150 kg. But overall, the performance or the power that able to deliver from your internal combustion engine lies closer to the baseline values. So the main objective is that you have to reduce the weight of the system, because when you are just moving to an hybrid vehicle variant, what actually happens is the overall weight of the system would get enormously get increased. because as you keep on adding battery to your system, already assume your vehicle is of already your vehicle is of 400 kg. That is your pure internal combustion engine, and you have been asked to get your internal combustion engine variant. You have been asked to get switch your internal combustion engine variant into an hybrid vehicle variant. Then what you actually be trying to do is you will be trying to club and battery plus motor combination either at any phi of any above phi of the one pivoting point. If that is the case, the weight of the system would get enhanced to a greater percentage. So the overall weight would get raised from 400 to 600 kg. So whatever the advantage that you gain from getting converted your existing weight into an hybrid vehicle variant would be drastically wasted because of this increase in weight. So for this main reason, what they are trying to do is they are just asking you to reduce the weight of the engine to somehow like closer to the existing model. So thereby, when you are just dealing with this engine downsizing, so your existing vehicle would weigh of around 450 kg and deliver the same power output. So thereby, you can just enjoy this add-on advantage of getting converted into an hybrid vehicle variant. So that is the reason why this engine downsizing is highly focused uh, in this particular research point of time. So one of the greater device that will assist you in converting your existing vehicle into a downsized engine is by make by means of your turbocharger, where with an aid of turbocharger you can just get an enhanced performance and reduce the overall weight of your system. And one among the combustion technique that we used to follow is the advanced combustion techniques. So apart from engine downsizing, we need to focus much more on the combustion parameters also to handle or tune the engine performance to a greater level. So talking more about the engine downsizing further, so advanced combustion technique is where is able to provide a trade-off between the emission and improving the efficiency of your existing internal combustion engine. And what is this advanced combustion technique? So the advanced combustion technique is a novel combustion concept which make it possible to reduce NOx and PM simultaneously. So this creates a major trade-off to most of the emission control norms, where either if you just focus much more on NOx, your PM would increase drastically, and if you focus more on PM, your NOx would increase drastically. So this is inversely proportional. If you focus on one particular parameter, the other would get increased to a greater extent. So now we need to rely on these both and make a trade-off and to get a possibly enhanced performance by downsizing the engine. So for this, what we need to do is we need to focus on the maximum combustion temperature. If you focus on the maximum combustion temperature, then you can just deal it with the reduced NOx emission. And when you are just focusing more on the equivalence ratio, that what talks about the fuel and the air interaction. If you are just focusing more on the fuel and the air interaction ratio, then you can just play with the particulate matter or the soot formation in your existing internal combustion engine. So in the combustion chamber, during the combustion process, by retaining the acceptable thermal and combustion efficiency, we need to rely on these two parameters. So this is the temperature versus equivalence ratio plot, which talks about the soot and NOx trade-off. So this is the profile for soot and this is the profile for NOx. So this soot is actually dominant in the temperature range of at 1800 to 2400, and whereas the NOx is making its role only after 2200 Kelvin. So you need to make a plot in between these two, and it doesn't impact majorly on soot and NOx. If you are able to design one particular combustion technique that doesn't play a dominant role in soot and NOx, then you can just clearly sustain that you are having a better engine to have a downsized engine for your pure hybrid vehicle variant. So for that only the advanced combustion engine combustion technology have take its role. So one is LTC, HCCA, PCCA, and the next one is advanced combustion techniques of RCCA. So the massive EGR low temperature combustion utilizing the charge homogeneity followed by homogeneous charge compression ignition engine and partially charged compression ignition engine. So all put together will assist you to convert your engine performance to a greater level and come up with an engine downsized to handle the hybrid vehicle variant. So this advanced combustion technology focusing on low temperature combustion talks about where the two major parameters that we are going to focus is that NOx and PM. So for playing with NOx, what is the device that we are going to focus is we are going to deal with the EGR. So just by enhancing the EGR percentage, you can just suppress the NOx level to a greater extent, and just by varying the fuel injection pressure, temperature, and mass, you can just play with the particulate emission. So these two is the major criteria by which you are going to focus on advanced combustion technology. One is EGR and second one is the fuel injection strategy. So the massive EGR with the low temperature combustion implies a charge mixing homogeneity would try to come up with a reduced soot and NOx trade-off. So the outline LTC region exists on the local combustion temperature less than 220 degree Kelvin and the local equivalence ratio ranging from nearly stoichiometric ratio to 4. If you just see the profile of LTC, so the overall equivalence ratio varies from 0 to 4 and it is well below the NOx generation pattern. So if you are just dealing with an enhanced EGR percentage, you can just slowly move away from the NOx formation. And if you are just optimally playing with your fuel injection, either in terms of mass, injection pressure, injection timing, you can just slowly get rid of this soot emission and play a zone in between these two cases. And thereby, you can just have a better combustion with a reduced emission parameter. So LTC seeks a simultaneous reduction of NOx and soot formation through decreased combustion temperature, because once the combustion temperature exceeds to 220 degree Kelvin only, it will produce an enormous amount of NOx. So once the temperature is well below, you can just play with a reduced NOx emission at a stoichiometric and locally rich air fuel mixture, and providing time for fuel and air mixing avoids high soot formation. So this providing time for high soot operation can be dealt with varying the injection pressure and injection timing. And dilution with either air or exhaust gas recirculation reduce the peak combustion temperature to avoid the NOx formation rates. Next one is the single fuel ACTs. So the most of the study that I have presented you talks about only single fuel ACT, and further we will just move into the dual fuel ACTs. So the reduction of NOx and PM resulting from near homogeneous mixture through use early injection timing and elevated gas EGR levels. So early injection timing, because of injecting the fuel early into the combustion zone, it will give proper time for mixing the fuel and air, and this excess EGR percentage will assist you to reduce the overall combustion temperature inside the combustion zone. So thereby you can just play with reduced NOx level, and here you can just deal with the reduced soot and particulate matter level. So the first one is homogeneous charge compression ignition engine. So in the homogeneous charge compression ignition engine, what they will be trying to do is, so I'm just reminding you once again, this is single fuel ACT. So homogeneous charge compression ignition concept present the early injection of the fuel during the intake process itself. So we will be injecting the fuel at the end of intake stroke. At the end of intake stroke, we will be trying to injecting the fuel into the combustion zone. So this is where the top dead center or at the end of compression occurs, and this is 90 degree before TDC, and this is 200 degree before TDC. If it is 200 degree before TDC, we are very much aware that 180 degree would be treated as one particular cycle. So if it is 200 before TDC, we are merely 20 degree at the later stage of intake stroke. So if you are able to deliver the fuel at the end of intake stroke, then you can just coin your system as homogeneous charge compression ignition engine. So the intake process takes place at a crank angle of 160 to 200 degree before the top dead center to make a homogeneous charge, but it is too far earlier for your fuel mixture, because at this particular point of time you won't have sufficient pressure and temperature. So that is one of the greater disadvantage focusing on HCCA engine. And the elimination of local air mixture and fuel mixture decreases. So thereby it results in reduced PM emission, while the low temperature combustion can be achieved with the reduced NOx formation. So with excess EGR percentage of 40 to 50 percentage, which is enormously high, when the EGR percentage is enhanced further, then all put together, it will just drastically pull down your soot and PM level to a greater percentage. So this green color talks about the HCCA combination, where you can just see the soot emission is very minimal and the NOx emission has been suppressed to a greater percentage. But one greater disadvantage is when the fuel is injected well prior at the end of your intake stroke, it leads to form HC and CO emission to a greater extent. It results in knocking to an enhanced level. So if the knocking is enormously higher, it results in higher HC and CO emission. So that is one of the greater disadvantages when you're just talking about uh, HCCA combustion, where you are trying to inject your fuel at the end of your intake stroke. And next one is single fuel EACT, where we'll be focusing on NOx and PM emission with an early injection timing and elevated EGR level. Next one is PCCA engine. So in case of PCCA engine, the diesel should be injected into the combustion chamber during the compression process. If it is HCCA, we are trying to inject the fuel at the end of your intake stroke, and in case of your PCCA engine, you are trying to inject the fuel at intermittent distance of your compression stroke. So this is your top dead center, whereas which is 360-degree, and we are trying to inject the fuel merely 90 degree before the top dead center, and either it can be multiple or split injection. So this split injection would have a varied injection timing, mass, and pressure. So this would be able to control the PM emission formation to a greater extent. But in the earlier stage, we are trying to inject the fuel at 200 degree before TDC. So when you are just making your injection over here, you can just deal with reduced HC and CO emission, and the EGR percentage is more or less similar. So the EGR percentage is more or less similar of uh, 30 to 50 percentage. So if you're just dealing with PCCA engine, here you can just see that you can just slowly get rid of your HC and CO emission. So the HC and CO emission is dominant at the temperature range of 1600 to 1800. So where because of oxygen unavailability and low temperature, flame quenching might happen. So dominantly the HC and CO emission would play a key role in this low temperature region. But when you're just dealing with this PCCA combustion, here you can just slowly step off from your HCCA and move further and optimally learn in a local equivalent combustion ratio, equivalence ratio ranging from 1 to 3. So here you can just see the overall percentage of soot and NOx formation has been completely eliminated when you are just dealing with your HCCA combustion. So it is having a narrow equivalence ratio bandwidth varying from 1 to 2, but the presence of larger combustion temperature, NOx would be produced at a minimal level when you are just dealing with HCCA. So what is the major outcome of these two studies of HCCA and PCCA is, in the existing internal combustion engine, you are able to incorporate two devices. One is an EGR setup, and next one is an computerized injection setup. Then you would be possibly able to create an advanced combustion technology, either it can be PCCA, HCCA, or CCA variant in your existing vehicle itself. Just by varying the injection timing, you should vary the injection timing, pressure, and the injection mass percentage in all the cases. Talking about the existing conventional diesel engine combustion, CDC could control the combustion phase by adjusting only the injection timing near the top dead center. We won't move further from this particular case. You might have seen a number of articles by varying the injection timing from 23 to 27 or 30, and injection pressure varying from 200 to 400. Talking about single cylinder engine. So just by varying this, they are trying to make a trade-off between NOx and soot to a greater level, but it is not much more efficient by using a mechanical device to vary the injection timing and pressure. So this talks about the wall timing diagram, where the maximum combustion temperature is extremely high in CDC condition because of higher release rate during the short combustion period, and the reaction that cause higher amount of NOx to a greater level. So when talking about CDC, it results in higher soot and higher knocks to a greater percentage. So just to get rid of this particular situation, they have just come up with LTC, PCCA, and HCCA based combustion. And this is not the latest technique that is available currently now. So the single fuel ACTs have many obstacles in the real world condition. So if it is HCCA, you are trying to inject your fuel at 200 degree before TDC. So that is in your intake stroke. And if it is PCCA, you are trying to inject your fuel in your compression stroke. So ACDs has difficulty to control the combustion phase, maintain the combustion stability, and expand the operating range towards the high load condition. So moreover, they produce an high amount of NOx and the carbon monoxide emission because when you're just lying closer to the low temperature zone with a very low local equivalence ratio, it results in higher CO and HC formation. So that would also once again pull back your thermal efficiency to a greater level. So we need to play an optimized zone in this particular region. So that is not able to achieve with a single fuel ACT. So for that, they have come up with the next generation advanced diesel engine combustion. So this gives you the brief outline of the advanced diesel engine combustion technique as of now. So it was in the 1890s, the SI engine and the diesel engine was commercialized to the automotive mankind. As I said earlier, it was in 1893 in the previous history slide we are discussing. So the internal combustion engine based vehicle was commercialized. And after that, people have tried to incorporate towards other direct injection, high pressure injection, variable valve timing, EGR, catalytic converter. All these invention has been done to a greater level. But the idea of HCCA was initiated in 1983, and the idea of PCCA was initiated in 1995. But for commercialization, it took merely next 20 to 25 years, and it was in 2007 the commercial HCCA engine was introduced to the automotive market. But in 2011, the University of Wisconsin has come up with an further advancement in this advanced combustion concept with a dual fuel strategy by the name of reactivity control compression ignition engine. So that is what is RCCA. So the greater disadvantage of single fuel ACT can be compensated or handled by this dual fuel ACTs, where dual fuel ACTs was introduced as an alternate to single fuel ACT in order to better control the combustion phase by utilizing two different reactivity fuels. As the reactivity fuel is single, it was very tedious to control the combustion. So thereby they have combined two different fuels to make a trade-off between the NOx and PM. So talking about RCCA engine and uh, pilot ignited dual fuel combustion engine. So with this dual fuel PCCA engine, it can be making use of a low reactivity fuel as a secondary fuel and your high reactivity fuel as your primary fuel. So your diesel will be injected as like in your uh, at the end of your compression stroke, but along with your intake stroke, you will have any low reactivity fuel. So this low reactive fuel, as of this particular case study, I have just considered compression ignition, compression natural gas. So where if it is dual fuel PCT, the CNG would be injected along the intake stroke nearly 200 degree before TDC, and your diesel would be injected closer to TDC. If it is injected closer to TDC, then you can just coin your engine as a dual fuel engine. So you can just see an enormous amount of research papers that has been reported with the dual fuel engine. So the dual fuel engine is nothing but a modified conventional diesel engine combustion mode. So if it is conventional diesel engine combustion mode, you cannot vary the injection timing from 20 degree before TDC to 25 degree before TDC. You won't move further this particular point. But for RCCA engine, you need to incorporate a separate injection system to vary the injection timing from top dead center. That should be merely 40 to 50 degree before top dead center, and this should be not a single fuel injection. It should be a multi-fuel injection with varied injection timing, pressure, and mass. If they're able to achieve this, then you can effectively control the combustion phase in a brief manner. So RCCA could control the combustion phase with fuel reactivity stratification and the fuel mass ratio between high reactive fuel and low reactive fuel. So the process involves the introduction of low reactive fuel into the cylinder to create a well mixture uh, charge of low reactivity fuel and air, and it would be coupled with the enhanced EGR percentage also, and all put together the high reactivity fuel will be injected at the end of the compression stroke or closer to it to create multiple injection, or either it can be a single injection to create the ignition. So this is how the dual fuel advanced combustion technique was introduced to the automotive market. So RCCA is a dual fuel engine technology. So that was developed by University of Wisconsin, where I have just presented the link also on their engine research laboratory in 2011. So which is not a major difference from your existing dual fuel engine. So in case of your reactivity control compression ignition engine, CNG will be injected into your intake stroke. But whereas the diesel would be not injected closer to TDC, it can be injected at any crank angle well after 90 degrees. So it can be 45 degree to 60 degrees. And it should not be a single injection, it should be a multiple injection. So Dr. John reported that the RCCA combustion could control the fuel combustion phase with fuel reactivity satisfaction. And both LRF and HRF are supplied into the combustion chamber at the earlier stage. The start of combustion is determining depend upon the chemical kinetics of whatever the fuel that you are going to use, and the fuel mass ratio between the LRF and HRF is the major determinant of the combustion phase. When moving further into the combustion phase, you need to focus much more on what is the mass percentage that you are going to inject your low reactivity fuel and high reactive fuel, and how you are going to split it and inject it to that particular scenario. So this what talks about the reactivity control compression ignition engine. So these are all advanced combustion techniques with dual fuel ideology. But this is also having a greater impact on lower thermal efficiency and HC and CO formation. At high loads, the excessive pressure rise generates because of auto ignition of the gasoline in the compression stroke limits RCCA formation. Because what we'll be trying to do is we'll be supplying the CNG or gasoline in the intake stroke itself, and because of any unknown heat source, it might be get ignited. So it might create an auto ignition well before the earlier injection itself, and that might result in certain knocking, or it might result in an enhanced HC and CO formation. So this problem could be solved by adding an higher EGR rate where the temperature can be controlled to a greater extent, and the air management system limits the ratio of 50%. So when you are just coupling 30 to 50 percentage of EGR to your existing system, then you can handle this excessive pressure rise issue related with your RCCA. And talking about the low load condition, it would be dominantly deal with higher HC and CO formation. So there is no greater research progress in particularly in this low load condition, where because of higher HC and CO formation, the overall thermal efficiency would dominantly pull down uh, for your even advanced RCCA engine. So let me just walk through the pilot ignited dual fuel engine. So if it is pilot ignited dual fuel engine, so your diesel engine would be closer to the top dead center, where based upon one of the recent literature, the low reactivity fuel through the intake port during the intake process would be injected, and the high reactivity fuel would be injected through the combustion chamber, and thereby the ignition process would be ignited. So the low reactivity fuel will be already in your combustion chamber, and when you are just injecting your high reactivity fuel, because of this air fuel interaction and the high reactivity fuel low or self ignition temperature, the combustion progress would initiate. The greater disadvantage is, even though when you are just dealing with dual fuel, you won't be able to control this primary fuel to a greater percentage. So that is the reason why the RCCA engine has completely suppressed the dual fuel engine at this particular point of time. Thus, limiting the HR of injection is the major determinant of the combustion phase. So in this particular case, the injection of your primary fuel mass plays a key role in your dual fuel engine concept. There is stringent emission norms, particularly Bharat Stage 6 or even Euro Stage 6. For even this Euro Stage 6, Now they are just moving with the D variant. So they are having a very stringent emission norms of NOx should be at zero point 0.4 gram per kilowatt hour and PM to a percentage of 0.01 gram kilowatt hour. So this is a very stringent emission norm. So to rely on this for either your internal combustion engine or for your hybrid vehicle variant, you need to drastically stick on with this engine downsizing by advanced combustion techniques. So apart from having this advanced combustion technique, you can't stick on to this emission norms at any particular point of time. So this emission reduction in your passenger car with the RCCA plug-in vehicle technology can be briefed up with this particular pictorial representation. So this is the pictorial representation of your hybrid vehicle drivetrain, where rather the battery plus electric motor combination can be placed well before the internal combustion engine or before the clutch, after the gearbox or at the end wheels. So for this particular study, we can just take the P0 combination. So normally this P0 combination is known as the base design. So that is built alternator starter hybrid powertrain. So in which a small electric motor replaces the traditional alternator. So just removing the alternator in your existing vehicle. So this is nothing but the micro hybrid vehicle. So just removing the alternator in your existing vehicle, what we'll be trying to do is we'll be trying to clump a battery, an inverter and motor, and by making use of a belt drive, we'll try to connect it to this existing engine. So this is what is the base or PBO combination. So in most often cases, the study would be conducted in the worldwide harmonized light vehicle test cycle. Make it clear, this is mostly designed for only internal combustion engine. But when you're just coming up with and hybrid vehicle variant, the change that you need to uh, make a note in this worldwide harmonized lightweight test cycle is that the main constraint imposed during the cycle is that the battery charge level at the end of the cycle, the battery charge, what is the SO state of charge at the end of the cycle, must be higher to the state of charge at the beginning of the test. So whatever the charge that your battery have, either at the end of the cycle, based on whatever the cycle that you prefer, either it can be worldwide harmonized or EDC, whatever the cycle that you, Europe based cycle or Japan based cycle, whatever the cycle that you prefer, at the end of the cycle test, it should be noted that the overall state of charge must be higher than what is the state of charge at the earlier level. It can be either equal or higher. So once it is happened or once this particular point is achieved only, you can just assume that your vehicle has passed the test cycle. And this is further branched out as the charge depletion mode and the charge sustaining mode. So the charge depletion mode says that your battery state of charge as is zero point 0.1 in the initial case, and you will be draining your battery to the range of 0.3. So in the initial driving cycle, you will be only running in pure EV mode. And once the battery state of charge get closer to SOC, the internal combustion engine would be started and you will be trying to maintain the same SOC throughout the cycle. So you can just try to drain certain amount of power from your internal combustion engine and charge it. But when you're just dealing with the charge depletion mode and charge sustainability mode, if it is a charge depletion mode, the electric motor is mainly responsible for the electric propulsion. So that is the battery state of charge varies from 1 to 3. So till this particular point of time, your electric vehicle will be electric motor and battery will be only propelling your hybrid vehicle, and your internal combustion engine will be completely switch off. And once the state of charge is getting closer to 0.3 or close to it, your electric vehicle will be switched off and your internal combustion engine would be in an on condition and you will be asking to maintain at this particular point of time. But in real time case, as the battery has been fully depleted to a lower limit of SOC around 30%. In the previous mode, the internal combustion engine is turned on and used to propel the vehicle to keep the battery state of charge within the small window of around 30%. So taking is as the base percentage. Once the cycle is completed, it should closely result in 0.3 SOC or 30% of SOC, or it should say well above. If that is the case, you can just assure that you have just passed the driving cycle test. And next, I have just given you a combined study of these advanced combustion techniques with single and dual fuel ACTs. If it is a CDC, your diesel is injected closer to the top dead center. And if it is HCCA, you are trying to inject your fuel uh, well before the compression stroke. That is, you are just trying to inject your fuel at the end of your intake stroke. And if it is in PCCA, either it can be single or multiple injection. So that is, you are just trying to inject your fuel in the mid of the compression stroke. So these three talks about the single fuel ACTs, and this two talks about the dual fuel ACTs. If it is a simple dual fuel, you are just trying to inject the diesel just closer to the top dead center. And if it is an RCCA, you are just trying to inject the diesel in the mid of a compression stroke. Either it can be single or multiple injection with varied injection pressure and timing and mass. And in both the cases, the CNG or any low reactivity fuel would be injected along the intake stroke. So this pictorial representation talks about the CNG percentage variation and the start of injection of your diesel. If it is an HCCA, it is well before the compression stroke, that is in the intake stroke. So it is minus 200 degree from the 360 degree. And if it is PCCA, it is in the mid of compression stroke. And if it is CDC, it is closer to the top dead center. And in the x-axis, it talks about the percentage variation of the CNG. For all these three, the percentage variation of CNG is 0. But talking about dual fuel PCC, so this dual fuel, where in case of RCCE, it is just nothing but the resemblance of your PCCA, where only the CNG percentage is varied. And the pilot fuel the conventional diesel engine combustion and dual fuel engine are more or less the same. Only you are just making use of the CNG or the low reactivity fuel injection to the existing combination. So this what talks about the dual fuel engine and RCCA engine. And here I have just listed out the injection timing variation and the CNG percentage variation. And in the existing engine setup, apart from the existing device, you need to have an EGR and a common rail injection system and a CNG injection. If you're able to handle with these three devices in your existing internal combustion engine model, then you can just convert your vehicle into either single fuel ACT or dual fuel ACT, focusing only on combustion. To convert your vehicle into hybrid vehicle variant, you need to incorporate a motor plus a generator concept. So thereby you can just convert your vehicle into an hybrid vehicle model. So I hope you're just running out of time. And in case of your experiment analysis in this particular case, first you will just focus on the combustion parameters. So in case of the combustion analysis, so this pictorial representation talks about the crank angle 50 data. So if the crank angle 50 data is closer to the top dead center, so if it is lying closer to top dead distance of either 5 to 10 crank angle degree after the top dead center, then you can just assure that your thermal efficiency would be enormously high. If you just see this very clearly, the crank angle variation of your CDC and RCCA lies closer to the 5-degree crank angle, but for PCCA and pilot fuel dual fuel, you can just see that pilot dual fuel, the percentage of crank angle CA50 formation or occurrence is too far from the top dead center. If that is the case, the thermal efficiency would drop to a maximum level. So that can be assured very clearly in the upcoming slide also. And next one talks about the ignition delay. As you are just igniting the fuel or injecting the fuel well before the compression stroke, that is in the intake stroke, there is a huge possibility for a misfiring or quenching. So this result in enhanced ignition delay occurrence for your HCCA engine, and it can be even reduced when you are just switching over to the PCCA engine, and it can be even further reduced when you are just switching over to CDC or either it can be dual fuel PCCA or RCCA. So whatever the case, when you're just moving closer to the top dead center, you can just see the ignition delay can be drastically reduced. And talking about the burn radiation in a parallel manner, so the burn radiation is sufficiently good when you're just dealing with uh, the CDC and pilot fuels PCCA, but the burn duration is enormously high for HCCA and PCCA. If the burn duration is higher, it results in lower thermal efficiency. And if the burn duration is shorter, it results in higher thermal efficiency. So the duration between CA5 and CA90 talks about the occurrence of the burn radiation in the throughout study. And next, it talks about the combustion stability. So the combustion stability describes the COV IMEP formation. If the COV IMEP formation lies between 5 to 10%, you can just assure that your engine doesn't result in any misfiring condition. If it exceeds the percentage of 5 to 10, you can just clearly assume that there is an higher possibility for the formation of misfiring. The blue color region is listed out in the region of just 5 to 10%. So if the region is of 5 to 10%, it doesn't result in any misfiring condition. So either it can be dual fuel PCC or CDC, it result in uh, a better combustion stability. But when you're just dealing with PCCA or HCCA, as the fuel is injected well earlier, it result in a very low combustion stability because of an higher misfiring possibility occurrence might happen. And next one is the noise and engine vibration. So the noise and engine vibration can also be determined by the maximum pressure rise occurrence with the crank angle degree variation. So if the maximum pressure rise is under 10 bar per degree crank angle, then you can just assume that the noise and vibration occurrence can be very minimal as of compared to any case study. But in the overall case, this result in very higher noise and engine damage, because in this complete case study of either single fuel or dual fuel PCCA, the average level of crank angle variation exceeds the 5 to 10 bar crank angle per degree variation. So throughout the above scale, you can just assume that it results in higher noise and engine durability scenario. Next one describes about the NOx and PM trade-off. So this is why we are just mainly moving over to uh, the advanced diesel engine combustion concept for your hybrid vehicle. So for NOx emission, when you're just dealing with pure CDC, it results in higher NOx emission, because you won't be able to deal it with excess EGR and of above 30 to 40% and with varied injection timing. So when you are just slowly getting switched over to PCCA or dual fuel combustion concepts, you can just drastically reduce the NOx level. So whatever the NOx level that we have suggested is of only 0.4 gram per kilowatt hour. So only in these particular region you would be able to achieve these 0.4 gram per kilowatt hour. That is by means of either PCCA, HCCA, or dual fuel. Particularly in this particular zone, you would be able to achieve the zero point 0.4 gram per kilowatt hour. And similarly, focusing on PM emission. So the PM emission, whatever is suggested in Euro 6 or BS6 norms talks about, it should be of 0.1 gram per kilowatt hour. If it is 0.1 gram per kilowatt hour, it can be achieved by CDC and dual fuel PCCA just by varying the fuel injection quantity. But when you're just dealing with PCCA and HCCA, because of misfiring issues, there will be certain higher HC and CO formation, and it can also be addressed because of the very low temperature occurrence in your PCCA and HCCA concepts. And talking about the unburned hydrocarbon and carbon monoxide emission. So PCCA and HCCA results in higher CO and HC and CO formation, because you are just trying to inject the fuel well prior, and at this particular point of time you won't have sufficient temperature and pressure inside the combustion zone. So that might be one of the reasons why the uh, HCNCO formation is enormously high in this particular case. But when you're just dealing with the CDC or dual fuel PCCA, it results in a very low HCNCO formation. So this says that the thermal efficiency would be higher when you're just dealing with the CDC or um, dual fuel combustion concepts. And next, talking about the engine thermal efficiency. So the engine thermal efficiency is higher for your dual fuel PCCA and CDC based combustion, and the fuel consumption is also in closely related with it. And whatever the values mentioned over here is the indicator thermal efficiency. And because of this split injection and dealing with the variation of mass of your low reactivity fuel and high reactive fuel, you can just effectively monitor the combustion phase and burn duration to a greater percentage. And talking about the in-cylinder pressure and heat release rate, as you are just making use of split and dual injection, you can just see the two reactive variation or two peaks occurrence in your heat release rate profile for your dual fuel combustion modes, where because of first flame propagation, it might result in a small peak in your low reactivity fuel region, well closer to your top dead center, and nearby the top dead center, you can just face the actual peak of your high reactivity fuel combustion. So this gives you the HCCA base combustion for your low, medium, and high loads in a brief manner. So to have a conclusion or comparison with the different combustion techniques, when you're just dealing with the pure conventional diesel engine combustion mode, the NOx emission is enormously high. When you are just focusing on PCCA, HCCA, and the dual fuel concepts, you can just try to step down from the NOx to a greater level. But when PCCA and HCCA, it results in higher particulate matter emission because of you are having higher HC and CO formation. So here, based upon the emission standards, dual fuel PCCA wins the race with reduced NOx and PM emission. And focusing on the thermal efficiency also, it is having a better thermal efficiency than your conventional diesel engine combustion, and it's an indicator thermal efficiency, and overall combustion efficiency also well closer to 100%. And the misfiring possibility is also very minimal when you're just dealing with the dual fuel PCCA engine. So as of now, for an hybrid vehicle, whichever is coming through the market, might be deal with this dual fuel PCCA or single fuel based advanced technique by varying injection timing, injection pressure, and injection mass percentage with an included EGR percentage to downsize the engine and resulting in a better performance. So the major takeaway is single fuel ACT would result in low NOx and PM, and it would be very hard to control the combustion phase. It result in low thermal efficiency and higher CO2 emission, and it is limited for only the low operating, low load range, and result in higher NOx and CO. Talking about dual fuel PCCA, it result in low NOx and better combustion phase, high thermal efficiency, and reduced CO2 emission and higher level of HNCO formation. I hope I have concluded the session as per the time mentioned, and I hope I didn't bore you much for past 1 hour and above, and I have given my perspective on the hybrid vehicle technology and recent research progress that is carried out in hybrid vehicle technology focusing on engine downsizing. So now I have given listed out certain reference and research articles that I have handled to prepare this particular presentation, and now the session is open to the audience. So if you have any further clarification regarding this particular presentation, you can just ask us off now. And herewith I have mentioned you my name and email ID. If you have any further queries regarding this, you can just ping me through this mail ID or contact number at any point of time. So now the session is open to the audience. Thank you.
Good evening, sir.
Good evening, sir.
Sir, in the water electrolysis system,
Okay.
which material positive and negative terminal using nowadays?
I couldn't get you clearly, sir. For
Water electrolysis system,
okay.
which material using positive and negative terminals.
Oh, I'm not very much clear about it.
Okay. In the electrolysis system, which catalyst using nowadays, sir?
We are not focusing much more on the electrolysis and catalysis. So we are just trying to combine, make alive our existing internal combustion engine by enhancing its performance using various technique, and just we are trying to club the in electric motor and generator concept to focus on the hybrid vehicle variant.
Okay,
And
sir.
our major focus is on thermal management on the battery system
Batteries.
over here. Yeah, we
Sir,
will try to
your
charge and discharge the battery and try to understand what would be the impact on fast charging and how much amount of heat is liberated because of the CC and CV. So
okay,
how
sir.
much amount of heat is liberated because of it, and how we can effectively control it and make better battery safety. So that's what we are just focusing in our research lab. And
Sir,
and
battery thermal management system, you are
okay.
focused on phase change material or cooling system?
Sir, we are just working on hybrid techniques. So we are just focusing both on phase change material and using liquid cooling also.
Liquid cooling also. Coolant,
Yeah.
any special coolant using?
As of now, we are just focusing on phase change material with the graphite particles. Along with the liquid coolant, we are just working on with the ethylene glycol with the nanoparticle additive to understand the heat liberation from the battery.
Okay, sir. Okay, thank you, sir.
Okay, thank you.
Any other question from the participant sides? I think no more question are there.
Okay, sir.
Thank you, sir. Thank you for explaining the engine right from 1892 to 2021, all the evolution stages of the internal combustion engine and their uh, mixing with the hybrid technologies also.
Yes, sir. Thank
It
you.
was
Thank you
very
very much.
informative session, sir.
Uh,
We are
uh,
pleased to have you with us. On behalf of
yeah.
NIT Srinagar, I thank you and thanks a lot to giving us your valuable time.
And it give me really great pleasure to deliver a lecture to this particular forum. I would like to thank the management, principal, head of the institution, and the organizer for giving me a great opportunity to share my small perspective on hybrid vehicle technology to the forum. And I believe it doesn't bore you much for past 1 hour. And if you have any further clarification, you can just ping me through this contact number or mail ID at any point of time. Thank you,
Sure,
sir.
sir, sure. We are also looking forward to hear you again whenever possible
Yeah.
in our next series.
Yeah, sure, sir. I'd like to happily collaborate with you in the upcoming program also. And if you have any further research ideas on this hybrid vehicle technology or battery thermal management in EV, myself and my research team would be happy to collaborate with you.
Thank you once again, sir.
Thank you very much. Have a great day.
Thank you. Same to you too, sir.
Can I leave the meeting, sir?
Yes, sir, you can, sir.
Okay. Thank you.
Thank you very much, dear participants, for your unwavering attention throughout the presentation. We will have the day 4 of our FDP from tomorrow, 9:30 a.m. Thank you and have a nice day.